All right, so welcome back. Hopefully you had a good weekend, first home game weekend. And last time we were just about to finish up conditionals with this program that we were writing to determine what the proper decibel level is, or describe a decibel level. From 0 to 60, it's quiet, all the way up to 111 through 194, which is dangerous, and then undefined if it's negative or 195 and up. And we just about finished the program, basically. And there's not really any other improvements that I would make here, other than going back to the drawing board and saying, well, now that we've simplified each one of these ranges, right? Do we really need to round anymore, right? What if it's 60.5? What will happen, right? If it's negative, then fine. This is false. If it's 60.5, this is false, so this doesn't occur. If it's 60.5, then this is false and it doesn't occur. Now 60.5 is decibel, right? But it does change the behavior, because 60.4 is now conversational, whereas before we rounded down, right? So we would change the behavior if we didn't actually round. So something to keep in mind, that a design decision at one point might, and then changing that later on might completely change the behavior of a program. What I wanted to do to finish this up is change it so that we are not doing this interactively. Excuse me. Remember that when we run the program, it prompts us for a decibel level, and then we enter 10.5, and it says it's quiet. Right? What I want to do is I want to change this so that it's command line arguments. So to do that, I'm going to go ahead and group these two things together, and for now, I'm going to comment them out. If this were an actual program, I would, of course, delete these entirely, because remember, that's cruft. That's garbage that should not be in your code. It's dead code, okay? But what I'm going to do is, instead of prompting for input, I'm going to check to see, did they make the correct number of command line arguments? If argc is not equal to the ones I expect, then I will issue an error message instead. Provide a decibel level, and then I'll quit on them. Exit 1. Okay. Now, what should this be in C? I'm expecting one command line argument from the user, but in C, remember how many command line arguments are given to me? 2 in this case, because the first one is always the executable file name. So if it's not equal to 2, then I will quit on them. Okay. Now, let me go ahead and recompile this. Actually, no, we're not done yet. Sorry. And so we need to read in the decibel level here, and that's going to be argv sub 1. Argv sub 0, remember, is the command line argument. Right? Now, is that correct? No. Let's go ahead and remember, you should always be using your wall flag, right, and the LM flag, because I'm using a round here, to determine is something wrong here. Right? And in fact, it's an error. It's not just a warning. Right? The error here is, well, wait a second. This is a char star, which is C's way of saying that this is a string. Right? It's a char star up here. But you're trying to treat it as a double. Right? What do I need to do to treat it as a double? Convert it to a double. Decibel is equal to alphanumeric 2 floating point numbers. You did this in your... you probably did this. You wouldn't have done this on your hack last week that's due today, but you would have done it on your lab last week, right? argv sub 1. There we go. Oops. There. Once I've got that, then I can go ahead and restore this to decibel. Right? Now, once again, let's go ahead and run. Okay, so sometimes it can't figure out the correct order of things, so demo.c. This is, I found that this is only true on Ubuntu, but there we go. The -lm flag has to go last. Right? And this is Ubuntu. This is the Linux version that we're running on Codespaces is Ubuntu. All right, so I get an error message if I don't provide a command line argument. Now let me go ahead and provide that command line argument, and I get that it's quiet. Remember that it is rounding still. Okay. One last thing. Let's go ahead and take this entire thing over here and just translate it or transliterate it into Java. Right, I'm going to go ahead and create a new class, and that new class will be called, what should we call this program? Foo? No. First of all, if we were going to name it foo, it should better be capital FOO, because that's how class names are done. In fact, you see up there, it's giving you a type name is discouraged by convention. Java types are usually upper camel cased. All right. So this is what, decibel determiner or whatever. Decibel is good enough. Okay. Now I'm going to cut and paste my C into this. All right. So I don't have a standard library. I don't have a standard Boolean library that's already built into the language. And I do have a standard math library, but I don't need to import it because it's part of the Java language already. So none of that works. None of that needs to be there. Documentation, author documentation, goes right above the class declaration. And there is no space here, right? So that's the style for Java. We don't have a main. We have a public static void main. Right? And of course, you could have auto-generated that if you really wanted to. When you create a new class, you can go ahead and check that box that says create a main, and it'll do it for you. And then you don't have argc and argv, you have args, right, as an array that we'll talk about later. So we don't have args here. Instead, we have args.length. That's the number of arguments that's provided at the command line. And I shouldn't be looking for 2 here, right? Because in C, the first one is always the executable file name, but in Java, it's not there. Why? Well, you called it decibel. You know what the executable file name is. So I should be checking for 1. System.out.printf, right? Oops. And then system.exit. I'll go ahead and I'll go ahead and get rid of my cruft entirely there. So I need to change this over to args of 0, right? But I don't have A to F. What do I have in Java? Double.parse double. There we go. All right. I don't have round in Java. Instead, I have to go to the math library, math.round. In Java, everything is a class, like decibel, or it belongs to a class. Right? In this case, the round function belongs to this math class. And if you want to check it out, right, that's like math.h, right? It's an entire class of, say, there's E defined, there's pi defined, there's tau defined, degrees to radians. Wow, that sounds familiar. Maybe if you're working on right now, radians to degrees, right? Et cetera, et cetera. Sine, cosine, tangent, et cetera, et cetera, et cetera. Right? By the way, how does it do sine? Did we really care? No. But it hands it off to another class called strict math. Right? And what does that do? Well, it hands it off to yet another class, fdlib sine compute. Right? And there is how you actually compute the sine if you're really, really interested. Okay? So, there. Lots of code just to compute sine, but lots of clever code. Remember that I'm just going to go ahead and, you know what? I'm going to go ahead and replace all printf with system.out.printf. And I'm going to replace all of them. Careful, I already did it once up here, so I'm going to go ahead and get rid of that. I should have done that very first, right? And I don't have to change anything. I don't have to change anything else, right? All the if statements are exactly the same syntax, exactly the same behavior. And you'll find that this is actually common in Java because the person, James Gosling, I think, created Java. And one of his design principles was it should look familiar. Well, what was familiar? C. Right? So he adopted as much as he could from C syntax. Okay? Let's go ahead and run it, and you'll see that it'll fail because we didn't provide a decibel level. Remind me how in Eclipse we provide a command line argument? Yeah. Under the run configurations, and then arguments, and 10.5. You can apply or just hit run. It'll automatically apply it for you. Remember that it's rounding, it goes up to 11, is quiet. Right? So there's not that much of a difference yet. Right? Let me go ahead and make sure that in the notes you have both of these versions if you really want them. There's the C version for you, and then here's the Java version for you. And copy, paste. And once again, these notes are pushed out daily to GitHub. That link is in the first week's retrospective. Any questions on conditionals? No? All right. You might be familiar with switch statements. We don't cover them. They're kind of brittle in both languages, and they're very, very limited. So if you want to learn about them, read all about them, but generally we would discourage their use. All right, so let's come back over here. Get rid of conditionals, and let's start talking about the next part, which are loops. All right. There we go. So often we need a way to repeatedly execute blocks of code. To do that, we need a loop. And for any loop, there are 4 basic elements. There's an initialization statement, because if you're going to repeat something over and over and over again, if you're going to run a lap around a course, right, you have to have a starting point. So every loop has to have a starting point. You need to know, do I continue to run for one more lap around this track, right? So that's called a continuation condition. If the condition is true, you continue for one more lap. If it's false, then you stop the race. Right? That's called a termination condition. Right? So the continuation condition is if it's true, you continue. The termination condition is when it becomes false. Okay? They're just complements of each other. Then you have an increment or update statement that makes progress towards the termination condition. Because if you're running around a track and you never make progress, right, then are you ever going to stop running around that track? No. It's called an infinite loop. Then finally, of course, you have a loop body, the code that executes for every iteration of the loop. That's what we call one run of the loop, or one lap around that track. It's an iteration, right? Or iteration for people with different pronunciation, right? We're going to look at 2 different kinds of loops, actually 2.5, I should say. The first one is for loops, and then the next one is while loops. And guess what? It uses the keyword for, right? And all 3 of the loop conditions, except for the loop body, are on the same line, right? The initialization, the continuation, and then the increment. There we go. Okay. Here's a very, very quick example. And you're going to tell me what this loop does. Oh, come on. There we go. For. Get rid of that. Int I equals 0, I is less than, say, 10, I plus plus, right? I'm going to printf, I is equal to %b and the line of I, okay? So all it's doing is it's iterating, right? We've got and printing out the result. We start at I is equal to 0. That's our iteration, that's our initialization condition. Note here the semicolon after that. I is less than 10. That's our continuation condition. As long as I is strictly less than 10, we will go one more iteration. And then we've got another semicolon there. I plus plus, that's new syntax. What does it do? Anybody? It adds 1 to I, and that's it. So we're going from 0, 1, 2, 3, 4, etc., etc. What does it print? What's the first thing that it prints? I equals and then what? 0, right? That's where it starts. Then it prints 1, right? Then it prints 2, 3. What's the last thing that it prints? 9, right? Why doesn't it print 10? Because 10 is not strictly less than 10, exactly. Right? And so we say that it breaks out of the loop, okay? It breaks out of the loop, and then normal control flow continues after that. Look at the style, too. The opening curly bracket is on the same line, right? The closing bracket is closing. Where did I put it? Is aligned with the F in 4, right? The loop body is indented. Loop body is indented, right? At one level. Spacing, right? There's no space between 4 and the opening parenthesis there, right? But we still have the opening parenthesis and closing parenthesis, okay? Note about the syntax, right? Both the initialization condition and the continuation condition end with semicolons. What about that increment condition? I++. Is there one after that? No. Yes, it is inconsistent. Don't ask me why, right? That's just how they wrote it back then, right? And so that's the syntax. If you tried to put a semicolon there, it would be a syntax error. It would not compile. Right? Let me show you over here in Java. I'm going to go ahead and get rid of whatever we were working on before. There we go. The only difference here is, of course, system.out.printf. And also, look at all that extra horizontal spacing, right? That's what Java does. So if you format it, just be consistent about it. Right? All I did was go Shift, Command, F to format it for me, and that's what it gave me. But if I were to try to put a semicolon here in either language, that's now a syntax error. It doesn't make sense to me. Right? It should have been consistent. Okay. The increment condition does not have a semicolon. It would be a syntax error. Other items. As you've already observed, I++ is the increment operator. It adds 1 to the variable I. Right? It's kinda like if I just did I is equal to I plus 1. Right? So it's just shorthand, right? It's called syntactic sugar, right? Is there a shorthand way of doing this? We do this all the time. Just go up by 1, up by 1, up by 1. So they shorthanded it so that you have an abbreviated version of it, right? Making the language a little bit more expressive. You do not have that in every language. For example, Python, just to be different, they decided, no, we're not going to have this, right? It would be really nice if you did, right? But Python said no. Swift, when it first came out, had this. And then they said, no, we need to be different. And they got rid of it for some reason, right? So don't ask me why. It's almost in every single programming language that I know of, right? All right, so there are others, right? Or actually, some other items here. Is I a great variable name? Not really, but it stands for increment, or later on when we will use it as an index, it'll stand for index, but it's common. I, J, K are usually used as increment variables. Short for index or increment, that's just the convention, right? They're terrible variable names, yes, but everybody does it, so if everybody does it, it's no longer terrible, right? All right, what about the behavior? The initialization is only executed once before the loop, right? The continuation check is evaluated at the start of each loop. That's why it didn't print 10. Let's come over here and walk through it again. I is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I is 9, right? It does the check right now. And so it says 9 is less than 10, so we execute the loop one more time. At the end, this is when I goes from 9 to 10 because the increment condition is done at the end of the loop. It jumps back up here to the continuation condition and it says, well, 10 is not strictly less than 10. So we jump out and continue after the loop. Right? So the continuation condition is checked at the start. And if it is true, it executes one more time. Right? If it is false, it terminates and escapes out, right? So note the increment is done at the end of the loop. And all 4 loops that I know of in any language will have the same behavior. The check is done at the beginning, the increment is done at the end, okay? We already saw that new syntax, I++. You can and probably will see this, I. It's called the prefix version, but why? Just keep it simple, use the other one. People like to use one or the other because they can do these little tricks where they can increment and then put it in an expression at the same time and save one line of code. But then you're always looking back, what was the behavior again, right? Which one was which? Basically the idea here is that when you use it in an expression, it takes on either the new value of I, so if it was 5 before, now it's 6, the value is 6, or does it take on the old value of I? I was 5 before, now it's 6, but it's still 5 for the purposes of that expression, right? And I think that that's the correct version, but I never get them correct, so which one is which, I don't even bother, right? I just write nice, clean code, right? But you do have other versions. If I did minus minus, what do you think it would do? Subtracts 1, right? You also have compound versions of these if you wanted to do something other than 1. If you wanted to add 2, if you want to go 0, 2, 4, 6, 8, etc., right? You can go plus equals 2. Now, it doesn't have to be 2. It can be 10. It can be negative 5. It can be an expression, I times 2 plus 5, right? It can do, you can put whatever you want on the right-hand side. Right? Well, you also have a minus version. You have a multiplication version. Right? So that one doubles it, actually. So if you go from, actually, if you start at 0, then it'll multiply it by 2, which is still 0. If you multiply it by 2 again, still 0, right? So if you start with 1, then it'll become 2. 2 becomes 4. 4 becomes 8, and you're going exponentially, right? You can also use division, but remember, this is truncation. This is integer division. So if you start out at 7, 7 divided by 2, it'll become not 3.8, 3.5, but 3 because of truncation. Okay? Let's go ahead and play around with it a little bit, since, let's go ahead and move this. This is the first thing I'm going to do is I'm going to put that 10 into a variable. That is much better, right? Because now you have a variable, that value is stored in the variable, that variable can change, et cetera, et cetera. Now the loop is only dependent on the n, the value stored in that variable. You'll come to know this as what's called the idiomatic for loop, right? It's idiomatic because it always starts at 0, it goes up to, but not including some variable, and it always goes up by 1. Right? This is probably going to be the most common line of code that you will write for the rest of your lives. Right? That's why it's idiomatic. Right? Remember those idioms? Right? The things that are just part of the language that you understand without thinking about it. Nobody thinks about it's raining cats and dogs. They just know, oh, it's raining hard. Right? We don't even think about this kind of loop because we write it so much. Okay? This is the idiomatic for loop. Now, if I did this and I changed this to 100, what would it print out? 0, 2, 99. Right? How can I play around with this? Well, let me go ahead and restore it back to 10. What if I went up to and including n? It'll start from 0 still, but it'll go all the way up to and including 10. When it becomes 11, that's when it no longer executes. Let me show you. System.out.println. Here's going to be a preview here. Actually, I'm going to cut and paste that. I wanted to show you that there would actually be 11 after the for loop here, right? But I can't. It's not compiling. What is it complaining about with respect to I here? I cannot be resolved to a variable. I declared it right there. But because I declared it inside those parentheses, I scoped it only to that for loop. Right? The variable I is born right here on line 9. It lives for every single iteration of this for loop. At line 12, that's when it's out of scope. Remember scoping? You're looking through a periscope and you can only see certain variables. This code can only see I within this for loop here. Now you might think, oh, well, the solution is to declare it outside. And don't do this. And now it does exist. Watch. After the loop, it is, I is equal to, save it. After the loop, it is indeed 11, right? Because I expanded the scope. Don't write code like that. You want as much limited scope as possible, right? Don't just jump up here to the top and say, I need a variable for this. I'm going to use them, I don't know, willy-nilly, right? No, use variables only where you actually need them. Scope them down as little as possible so that this is now invalid. Same thing in both languages, by the way. Very, very old school C, like, 30 years ago C, 35 years ago C, you couldn't do something like this. You had to declare your variable. You couldn't scope it down to just a for loop. You had to declare it before the for loop. 50 years ago C, 45 years ago C, you could not do something like this. Here, this is not C, so I'm not getting it. Int x is equal to 5, right? all your variable declarations had to be the first line of code in your function. Right? And you can still get this, by the way, if you pass in a flag saying pedantic, right? Be as strict as possible with old school 1970s C, right? And it would not allow you to declare a variable somewhere down inside of a function, right? We don't like that. We like modern programming languages, modern syntax, modern syntactic sugar. So this is how we're going to write our loops. Okay, oops. There we go. Okay. Let's play around this with a little bit more. What if instead I went up in increments of 3 plus equals, excuse me. Right. So it starts where? 0, 3, 6, 9, and it would go up to 12, but it wouldn't get printed. That's when it gets out, right? What if I did this? Go down by increments of 2. Yeah, what's it going to do? 0, then -2. -2 is still less than or equal to 10, right? So infinite loop there, right? Now, eventually it will come around because of underflow, right? If you go down to -2.147 billion, right, then it'll come back to positives, and you will eventually get, and that means that 2.147 positive billion is going to be greater than 10, and that's when it stops executing. We're only in the 7 millions now, so we've got a long way to go before that happens. I don't want to wait. And so what happens when you've got a runaway program like this that you started by hitting the play button? You kill it by hitting the stop button, right? Okay. What happens if you do this in C? Let me bring it over to our other IDE over here, and I'm going to go ahead and get rid of everything down here. And the only thing I need to change is printf. There we go. All right. GCC demo. By the way, the wall flag is not going to save you. Computers aren't smart enough to necessarily to figure out that you've got an infinite loop there. In fact, there's no computer that can do that. It's a result called the halting problem. You cannot write any other code to test code to see if it always halts on any input. Right? That's provable, that there is no such program. All right, so how do I quit out of this? There was no start button, so therefore there's no stop button. So instead I need to go to Control C. That kills whatever the current running program is. Okay? All right, no, we'll review this later on here. But you can play around with loops and figure out how they go up, they go down, plus whatever. Okay? All right. It is, how about while loops now? This is the second type of loop here. A while loop, it does not use the for keyword. Instead, guess what it uses? A while keyword, exactly. Right? Unexpected. Right. The main difference is that all three of those elements, the initialization, where you start your loop, the continuation, and the increment, they're all on separate lines. Okay? Let's go ahead and rewrite that same loop that counts 0 up to 10, but let's do so on int n is equal to 10. Let's do so using a while loop here. All right? So while I is less than n. There's the continuation condition. But one key difference here is that you cannot do this. Right? Where in a for loop, you could scope it down to just the loop. That's not possible in a while loop. What you have to do is you have to move that declaration up before the while loop. Right? Okay? That means that we can take advantage of that declaration and assignment at the same time to define our initialization condition. I will start at I is equal to 0. While I is strictly less than n, we'll go ahead and print it again. So let me grab that code. Right. There we go. Now, I've got the initialization before the while loop. I've got the continuation condition bound to the while loop, the while keyword there. Where's my increment? Yeah, I haven't written it, right? So it's optional. Right? What's going to happen here, by the way? Infinite loop just printing out what? 0, 0, 0, 0, 0 forever. Right? So let me go ahead and put in my increment condition at the end of the while loop. just to get the exact same behavior of my for loop, okay? Let's go ahead and grab that and go back to C maybe. All right. There we go. Nope, not search. What's that tool again that you can go ahead and correct all the white space with one command? A style demo.c. There we go. Flush it, and there we go. All right. So let me go ahead and compile this. And it'll print out 0 through 9, exact same behavior as before. But one of the reasons that you might want to use a while loop is because you have a little bit more discretion on when the increment happens. The continuation, like the for loop, is always done at the beginning of the for loop, or at the beginning of the while loop. But the increment here, that can be done at the beginning, it can be done at the end, it can be done somewhere in the middle if I had multiple lines. Right? I could put it wherever I want. How does it change if I put it at the beginning of the loop? I is 0. Is 0 less than or equal to 10? Yep. We come in, 0 becomes what? 1. And so the first thing that we print out is not 0, but 1. Fast forward, fast forward, fast forward. I is now 9. And we come back up to the while loop here. Is 9 less than or equal to 10? Yep. 9 becomes 10. What gets printed for the last thing here? 10. Because now it's 10, comes back up here as 10 less than or strictly less than 10? No. So it changes the behavior from 1 to 10. Right? And you have that, you have a little bit more fine control on when this increment happens, or if it doesn't happen at all. Right? Okay, so that's the bit, it's a little bit more flexible. You can put the increment anywhere that you want in the loop. If you don't, then it'll be an infinite loop. Kill it with Control C in C, right? Or the stop button in, or the stop button in Eclipse. Right? There we go. You cannot scope a counter increment variable to restrict it to just the loop like you can with a for loop. Like I said, neither language will allow you to do something like this. Okay. Well, first of all, you lose the ability to even assign it a value, right? But it's saying, no, you can't do something like that. Okay. So it's a little bit more flexible on the increment. It's a little bit less flexible on the scoping, right? In general, it's best practice to limit the scope of the variable as much as possible. So if you're looking, should I use a for loop or a while loop? Right? For loop is probably a little bit more straightforward. It's more, it's less flexible, yes, but also it means that you can scope your variables down a little bit more. So when in doubt, probably a for loop. But if you have your, that's not like a hard and fast guideline or rule or anything. Which one do you use and when? Right? It is a non-trivial fact that you can take any for loop and rewrite it as a while loop. You can take any while loop and rewrite it as a for loop. You do not need both loops in any language. Right? You can get by with just one of them. Right? And usually you can get by with a while loop. Right? So why multiple loops? Because we like flexibility. It's that syntactic sugar again. Right? If you only had one word in English for good, right, it would be a pretty boring language. Right? If you only had one word to describe anything, it'd be a pretty boring language. So we like to have our language full of metaphor, full of flexibility, full of nuance and meaning. Similar coding languages have syntactic sugar. Things that you can write like shorthand, I++. That's nice and sugary because we can write quicker, we can read quicker, and we can understand quicker. Abbreviations or syntactic sugar like, well, this doesn't really fit in naturally with a for loop. This doesn't really fit in naturally with a while loop, so I'm going to use one or the other. Here's an example, right? So here's we'll do it in C, right? And let me go ahead and go with int n is equal to 1, 2, 3, 4, 5, 6, right? Write code to determine how many digits are in n, ... Now, yes, you can go ahead and look at it and say 6, I'm done, right? Or print 6. System.out.print 6, right? But it's not always going to be 1, 2, 3, 4, 5, 6. Sometimes it could be 1, 2, 3, 4, 5, 6, 7. Sometimes it could be 1. Sometimes it could be 0, which is what? How many digits are in 0? Technically 1, the same as 1 or 9, right? So we're going to have to be careful on our code. 1, 2, 3, 4, 5, 6. Right? Is that big enough for everybody in the back? All right. All right, so ideas. First of all, think big brain math time right now. What is that one thing that you learned in high school that can quantify the magnitude of a number and give you the number of digits in it? Logarithms, right? So if you took the log base 10 of a number, it would give you within 1 the number of digits in that number, right? It's unfortunate because they don't ever teach you that that's the actual meaning, right? So how do they teach logarithms? Here they are, just use them. Yeah. Pretty much. All right. Well, why do we use them? Because it quantifies the magnitude of the bigness of a number, right? All right. So I could use log, but I didn't learn that in high school. So let's do something else. Ideas. Well, what if I had a counter over here in my? Yeah, go ahead.
You could loop through each individual part of this.
Right. So I could say, oh, 6. That's one of them. 5. That's another one. 3, 4, 5, and 6. You're counting the digits in it, right? So let's have a counter first. Int count. Right. Where should I start it out at first?
At
0. Okay. All right. Maybe that's off by 1. We'll figure it out later on as we troubleshoot this. Now, that idea of, well, here's one of them. Let's go ahead and throw it away then. Right? There's 2 of them. Let's go ahead and throw that away. There's 3 of them. Let's go ahead and throw that away. What operation was I doing? If you take 1, 2, 3, 4, 5, 6, and it becomes 1, 2, 3, 4, 5, what did you do to it? Yeah, you divided by 10, and then you got rid of the value because otherwise this would have gone up to 6, right? So I divided by 10, and then I threw away the fractional part. That sounds like integer division to me, all right? So let's outline this, right? Something. If there are still numbers, if there are still digits in n, then indent, divide by 10, right? And then increment the counter, right? There's my initial outline. So question, what kind of loop do you want to use here? Yeah, I was avoiding it at all costs, trying to say it, right? But it was like I couldn't figure out another way of saying it because it was so natural. While there are still digits in this number, right? You don't say for each digit in this number, because if you said it's for each digit in this number, you know how many digits are in the number to begin with, right? I want to know how many digits there are, so I'm putting the cart before the horse there. So while there are still digits in n, in other words, while n is still greater than 0. We will divide by 10 and increment the counter. I'm pretty confident that we can go ahead and write this now. While n is greater than 0, right? Divide n by 10. N is equal to n divided by 10. Is there a more compact, easier way of writing that? Divide equals 10. There we go. And then finally increment the counter. Counter is equal to counter plus 1. Yeah. Plus equals 1. Plus equals 1. Or even better yet, plus plus. There's this thing called code golf, if you've ever heard of it, right? Oh, sorry. Count, thank you. There's this thing called code golf. I can do that operation in 5 lines. I can do it in 2 lines. I can do it in 1 line. Well, I can do it in 1 line and only 10 characters. I can do it in 5 characters, right? And you get down to this, why? Because golf, the lowest score wins, right? And so the most compact program wins, right? It's usually a terrible program because it's incomprehensible and unreadable, but it works, right? All right, so printf. There are blank digits in blank. End. Right? there are count digits in n. We're not done yet because there are still several bugs, but let's go ahead and see if it works at least on 1, 2, 3, 4, 5, 6. There are 6 digits in 0. The 6 is correct. What happened to the 0? It got overwritten because we were divided by 10 the entire time. Right? So if you want the original, but you also want to manipulate it, what should we do? Make another variable. Original n is equal to 1, 2, 3, 4, 5, 6. Right? That's where we'll set it. And then n is equal to original n. Right? And instead of printing out the changed variable here, I will print out the original n. Okay, that works. Done, ship it. Now, hopefully as you learned in your lab last week, you know, if you're writing code to do the leap year, you'd better have at least one leap year test and one that's not a leap year test, right? And it's better if you have an entire series of unit tests saying, oh, this works and this works and this works great, they all work, right? Or I guess that's this week, sorry. That's tomorrow that you're gonna be doing that. You're gonna have, we give you 3 test cases, you have to write 3 of your own after you write the code to do that, right? So what's another test case that I should try? Well, what if it's only 3? Come on, there we go. That works. Is there something else I should try? Just one, all right? Like, let's go 9 even. There should be only 1 digit. Hey, that works. Remember we said 0 also had 1 digit. There's 0 digits in 0. That's what we call a corner case or an edge case, right? It all works until you get to the edge of the room, right? And then you can't quite paint that corner that much. So you have to take care of that edge case by itself, right? What we could do is we could issue a check here. If or n is equal to 0, that's one special case. That's a corner case or an edge case. Printf, there is, but even better grammar, right? There is 1 digit in 0. And be done with it. Exit. I'm going to exit with a 0 code here because everything was fine. There were no errors, 0 errors. All right? There. I didn't handle it in my loop here. I could have tried to rethink my loop and try to incorporate that one edge case into it so that my one loop rules them all. But why? If it's really an extraordinary case here, just like in math, there's always an extraordinary case at 0. 1 over x, as x approaches 0, it blows up, right? Not square root of 0 because that's valid, but weird things happen around 0, right? So it's a different edge case entirely. Right? Is there anything else I should check here? I checked a bunch of positive numbers, 0. Yeah. Does it work for negative numbers? 1, 2, 3, 4, 5. Now, the negative value there, the negative sign, is not a digit. So it should be 5, right? There's 0 digits in that. Okay. So what's happening there?
It's less than 0.
Yeah, it's already less than 0. Does this while loop execute at all? Nope. So we could change the while loop to be not equal to 0. What will happen if I divide negative 10 by 10? Negative 1, right? So I anticipate that this will work now in that case. There are 5 digits in there, right? But did I break anything? I completely changed the behavior of this while loop. Did I break it at 0? Probably not, because that's handled specially. Did I break all those positives? Let's find out. Okay, that still works. I don't know, does the single digit work? Probably, this is a simple enough program. But the point here is that if you write a bunch of tests, what I'm doing here is ad hoc testing. I'm just, compile, try this, compile, try that, right? And that's not the way to go about doing things in practice, right? That's the way that everybody starts out doing beginner stuff, and that's the way that you'll do it. But eventually, you'll see that in your lab this week that it's much better if you automate this, right? Because sitting there trying, yeah, that works, yeah, that works. Oh, that doesn't work, I broke that somehow. It's called a regression, right? You've regressed back because you You fix that bug over there, but by fixing that bug, you've introduced now 5 other bugs, right? And so automating this process is much better. In other words, writing code to test your code. Now, the first the first time that you'll be doing this is in your lab this week, where you're writing. It's kind of an informal unit testing because you actually have to write all the code to do it. We wrote half of it for you, and you just have to cut and paste. But then later on, you'll learn, well, why am I writing all this boilerplate crap? There's got to be a better way of doing that. Yeah, bring in a library to do it for you. Right? And for Java, that's going to be JUnit. For C, it's going to be CMaka. Right? And we always give you beginner code, starter code on all that stuff so that you can see how it works. And then just have to write your own test cases. A test case is simply an input, right? And an expected output. What's my expected output here? Int expected num digits would end up being 5. And what you would do is you write code. Here's my input, put it into this function or this program, you'll get your output. Here's the actual output, here's the expected output. Do they match? If they match, the test case passes. If they don't match, then the test case fails and you need to go back and fix it. It could be the case that your test case is wrong, right? There are 4 digits in 1, 2, 3, 4, 5. No, that's wrong, right? So you need to determine, is my code wrong or is my test case wrong? Or the worst case scenario would be that they are both wrong, but in the exact same way. In which case it passes. That's called a false positive, right? It passes, but it's because you made 2 mistakes instead of just 1. All right, that's what you'll be doing in your lab tomorrow with a leap year, and then we'll continue with loops on Wednesday.